طيب بسم الله الرحمن الرحيم. So we started talking last time about symmetric encryption. We talked about the properties for the symmetric encryption. We talked about the fuzzy structure and its properties and the limitation in terms of the key size, and then we detailed the specs for the first encryption algorithm, which is DES algorithm. So today, inshallah, we'll continue this discussion. As we said, the limitation for DES, that because it works on bit manipulation, bit level manipulation, it's highly complex, and actually in the assignment you will experiment with this a lot, with all these encryption algorithms, and you will appreciate more what we're talking about. So it's more efficient to implement this in hardware. However, still the limitation is in the key size. And as we said, nowadays you can actually have enough computations to break this algorithm in 1 hour on simple devices like cell phone. That doesn't mean that this is not usable by any chance, because as we said, if we decide as part of the protocol to renew the key every less than an hour, then we could still use this, right? But the risk is still there that you can break this using the many of the devices that we have nowadays. And that's why today we'll talk about triple DES, and the motivation behind triple DES is just to work on the limitation, on the direct limitation of this, because DES has a limitation in terms of key size, so let's work on increasing the key size. But if we increase the key size, the whole algorithm is designed based on this key size, so the idea is just to replicate the same algorithm 3 times, as we will see. It's simply replicating DES 3 times. That's why it's called triple DES. It's very, very simple. So this way we were able to triple the key size and increase the number of computations required to break. And of course, it actually it grows exponentially, because as you can imagine, just having 1 bit extra in the key, that means that the time required is double, right? So so by tripling the number of bits for triple DES, of course, the time required is exponentially increased. The problem with DES and triple DES is that they are efficient in hardware, but they are not efficient in software. And that's because of the bit level manipulation, because we know that software is not good in bit level manipulation. Many of the devices that use DES and triple DES, they tend to use more efficient hardware, which makes the computation fast, but it's actually rigid, and and that's why when they tried to solve DES, they came up with triple DES, which means replicate the same hardware chip 3 times. So if it's software, then it would be easier to reconfigure and restructure. But this implementation is always rigid to modify. And then we'll talk about AES today, which is it's considered like a revolutionary approach in fundamentally changing the algorithm of DES and removing or eliminating the bit level manipulation. Okay, and of course, by doing that, AES becomes more efficient in terms of software implementation, and that's why, as you can see, we can easily now change the key size without having to have lots of modification in the algorithm itself, because it's efficient in software implementation. So we talked about the complexity of the algorithm and the time required to break each one, and of course, by doing that, this is the time required to break it. However, if we look at quantum computing, of course, all these times become useless, because يعني these number of years, they will become seconds in maybe 1 minute or something, okay? But luckily, we have complete realization for a quantum computer so far, which make us at least safe, future safe at least for the next decade or so. So that's triple this, as simple as that. So it's just replicating the same chip or the same algorithm 3 times. So as we have discussed last time, each key here is how many bits? 56. Bravo عليك. So this key is 56, and these are 3 keys, so 168. So it's one thing we notice here is that the plain text is applied 3 times. And this means that for each one you have 16 rounds, right? So this means that the plain text goes through 16 times 3 rounds of trying to decorrelate the plain text from the ciphertext. And that, of course, increases the decorrelation and, of course, more robust in terms of security properties. So another thing to notice is that the keys, the keys are applied in a reverse fashion at the decoder side, which makes sense, right? And this is one of the tricks that sometimes students, they do in the assignment, very common. So K1, K2, K3, K1, K2, K3, and they see that the output is not, the same. So they feel there's something wrong. So the keys have to be applied in reversed order at the decoder side. Okay, very simple. There's no new thing here. Just replicating the same 3 times. So the triple DES has been defined as part of this FIBS document. Of course, we don't have to memorize the number. So NIST has approved the triple DES, as simple as it is. They approved it as the de facto standard or the recommended encryption algorithm, and they have deprecated DES as an algorithm, and they encouraged all the manufacturers to start using triple DES instead. So that's why in the upcoming chapters you will see a lot, all the security services and protocols, they tend to use either AES or triple DES. None of them actually uses. None of them uses this. Okay. Okay. So, however, of course, the triple DES was a quick and dirty, upgrade to DES, which is fine. However, they were actually looking for long-term solution, fundamental solution, which tries to increase the security properties, but at the same time reduce the complexity. So they have posted that challenge as a request for proposals for people to try to come up with a technique which has the same security properties of triple DES, however, with a lot less complexity. And many, proposals have been trying to achieve that objective, and that's when we came up with the ES. So we'll talk about this today. Okay, so that's the AES. So AES tries to achieve the same robustness of triple DES with 2 things: much less complexity and more suitability for software, which means that we should try to get rid of any bit level manipulation. Okay, we should try to have byte level operations which are more optimized to be done in software and hardware, of course. Okay. So, and they have, of course, specified more requirements just to be able to test the flexibility of the algorithm in terms of key size. So different key sizes. So they also specified the requirements for different key sizes. And the evaluation criteria in terms of security robustness, computational efficiency, minimum memory requirements, all of these have been part of the specification for the call for proposals. the one that won this competition or this call was the Regendile proposal, which, of course, it's clear from the name. So, so this proposal has been the one selected by NIST to be the standards for AES. Okay, so we'll talk about AES today. So this is the structure of AES. So similar to DES and triple DES, we also have key expansion technique. But one thing we notice here is that the key is 16 byte. As you can see, from now on, we will not see 6 bits, 56 bits. All of these are bytes, okay? So there is no bit level operations or manipulations. So we have here, the key expansion. For the key expansion, the key expansion converts the 16 bytes into 10 different matrices, two-dimensional matrices of 4 by 4. So 16 here means that you have 16 bytes. So they arrange the 16 bytes into 4 by 4 matrix, and they have 10 of these matrices for the 10 different rounds. Of course, we talked about this. So why 10 rounds? I tell you, why 16? So these have been like arbitrarily chosen based on certain level of trade-off between complexity and security robustness. Okay. So at the beginning, we do like 4 types of operations, and each of these operations you will find it's practically simple. It's very possible to be done in software or hardware. So the first one, which is done only once at the beginning and once at the end of each of these rounds, which is add round key. So the add round key is simply Vernam cipher. So it's just to get this matrix and the plain text, which is also 16 bytes, and XOR both matrices together. Just a simple XOR. And XOR, as we all know, is software friendly. So we can do it in software easily. So so the add round key is done once at the beginning and one at the end of each round. Other than this, we have 3 other operations, which we will talk about. So one thing we notice here, or we'll see it even in the code of the assignment, there is always the notion of course, the key state, and there is also the concept of state matrix. The state matrix is, again, the outcome of the matrix operation at every stage. So here, this is the state matrix, and after doing the substitute key, we have another state matrix, and we have another state matrix, and so on. Okay? Here, the substitute bytes, similar to the substitution that we've done. However, if you remember in this, we used to take 6 bits, right? And then we take the first 3 bits and so on and so forth. Here, no. Here, we do it at the byte level. And we'll see how it's done. So we use bytes as, for the lookup table. And the lookup table itself is, again, is universal, is well known. But the key thing here is that the substitution is done using like byte, using just bytes. So this will, again, speed up the software operation. The shift rows is actually circular shift. But again, circular shift is not bit level. So we'll see. So the circular shift is we shift bytes. We shift bytes, not bits, okay? Which again makes it software friendly, okay? And then using the mixed column. The mixed column is matrix multiplication. So we have the state matrix. So here we have a state matrix, okay? And we have another, again, predefined matrix. and we just multiply them together. That's it. Okay? So all these operations are software friendly. The main thing here is that, of course, you have to work on the analysis of the robustness of this algorithm from information theoretic perspective, and that's out of the scope of the course. So the key is after each state you need to measure the correlation, the probability of guessing the key based on looking at the state metrics at different level and so on, and then we prove the robustness of this algorithm based on this analysis. Okay, so we'll go deeply into these operations. So, of course, the add round key is just XOR. So it's just XORing, which is what we call a Vernam cipher. As we said, Vernam cipher has cool properties in terms of, if you know only the cipher text, then it's attack proof. But if you know one simple plain text, just one, then you can guess the key in one trial, O of one. Okay, we'll talk about this more today. So here, the substitute matrix is very simple, very easy. So if you look here, so we take, this is the state matrix after the add round key, of course. So this is how the state matrix looks like. And each of these is like 1 byte, 2 hexadecimal digits, right? So here we take this byte, we take 0, 0. So we look at the lookup table. So 0 and 0 is like 63. So we put 63. As simple as this. That's it. So each byte is used to...
add round key is, do we add the key to the plane?
Yes, it's like add round key, which means that the state matrix, we add the round key. The round means the expanded key, because the key expansion gives you 10 different keys. So we call this a round key. So the round key for this particular round, okay, we just add it to the state matrix. That's it. XOR it. Add means XOR. Okay. Okay. Same thing. So 3 and C, EB. We put EB. That's it. Very straightforward. And this lookup table is published. Okay, it's well known. Okay, so this substitute operation is very simple and straightforward. This is the shift rows. The shift rows again is a circular shift. Okay, so circular shift means that we look at the state matrix and then we take the first row, we don't do anything. Second row, we shift one left. So we shift this here, this here, this here, and this here. Okay? And then we take the second row and we shift it 2 times. We shift 2 positions. Okay? And this one is like 3 times, which means 1 to the right. Okay? Very simple. Okay? Very straightforward, yeah. So this will be the result of this, which we call it another state matrix. So after each of these stages, we have a new state matrix. So we keep accumulating operations on the state matrix to achieve another state matrix. And at the end, we straighten this state matrix, we flatten it to become the new ciphertext. That's it. And that's the mixed column. The mixed column is nothing but matrix operation, matrix multiplication. So we take the state matrix, we put it here, okay, and we multiply this arbitrary matrix to it. So, and the result will be the new state matrix. Any questions? So all these operations are straightforward. Okay. So in the assignment, of course, you will see the code of this. But the idea is that in the assignment, we should try to measure the performance and experiment with the performance of the effect of the channel, the transmission on these encryption algorithms. That's what you are going to focus on. But you will see the code of all these encryption algorithms. It's relatively straightforward. Okay, any question with AS? Okay, another topic which is also very important, which is called random and pseudo-random numbers. So here, what we are trying to do is that we are trying to generate a random sequence, okay? So the idea now, or the objective, is to generate a random sequence. So that's the simple objective. So what do we use this for? We use this in multiple ways, in many, many, many ways. Generating random sequence will help us to, for example, select the keys. Okay? So we use that to select certain keys, and we'll see this applied in many security services after that. We can generate what we call the initial vectors. We'll talk about initial vectors and what we use them for. So the generation of keys for RSA, for example, RSA is one of the techniques that we will talk about next. The generation of public keys or symmetric keys can be done using like just random sequence. But this random sequence has to have certain properties. This is the most important that we need to talk about. And if this random sequence needs to have these properties, what are the techniques that we can use in order to guarantee these properties? So first, we need to talk about the properties that need to be guaranteed in this random sequence, and then we'll talk about one simple technique that we can use to do that. So a number of key distribution scenarios, such as Kerberos, we'll talk about Kerberos in the next chapter. Random numbers are used for handshaking, so it facilitates the authentication. User authentication. So we'll see that. Okay. So in other words, this generating the random sequence such that this random sequence has these two properties. Okay. This particular function is used in many, many, many ways. Okay. Right. So this is the most important thing. But what are these properties? We have two major properties, and NEST actually defines, if some of you are familiar with that, the set of tests to apply on any technique that claims to generate random sequence. So the idea here is that first, this random sequence should be random. Should have uniform distribution. Okay? Similar to when we talked about the keys, we said that if we have a key of length n, then on average, how many operations I need to break that key or to guess that key? 2 to the power? 2 to the power n minus 1, right? صح كده? But that's if the key has uniform distribution. Okay? And by uniform distribution here, I mean that, for example, if I tell you that, or if you know that the key has a distribution of like this, or something like that, okay? Then in order to guess the key, you will always focus on the less properties or the other way around. As an example, if you know that this key has much more ones than zeros, okay? What are you going to guess? Number of zeros, because the number of zeros has less combinations, right? And I will try to permutate the position of these zeros in the key, which means that the rest will be ones, right? So if I know that the number of zeros is much less, then I will play on the zeros. If I know the other way around, then I will play on the ones, right? But if I know that the probability of 1 equals to the probability of 0, then I have no information. صح كده? So that's what when the key has this uniform distribution. So the probability of taking any value, any value, is the same. So a probability of 1 and equals to the probability of 0. So that's what we mean by randomness, true random, which means that the probability distribution is uniform. Okay? The other one is unpredictability. And by unpredictability means that, okay, so it is uniform, but if the key has a certain length, and I happen to know part of it, if I happen to know part of it, okay, will I be able to predict this part or not? Okay? For example, I know that the key, if it has 1 0, then most probably the one after it is 0 1. So this means what? This is another probability distribution now. This means that the probability of having 0 1, given the fact that I have 1 0 before it, is high. واضح كده؟ So this means that the key has some predictable patterns. Okay? So I want to avoid this. So we would need to avoid this from happening. So that's what we mean by unpredictability. So even if you know part of the key, you wouldn't be able to guess any other part of the key because they are totally uncorrelated. So the different parts of the key are totally uncorrelated. واضح? So knowing any part, it will not allow you to predict any other part. Okay? So that's what we mean by unpredictability. So the randomness means uniform distribution. So the distribution of bits in the sequence should be uniform, which means that the frequency of occurrence of ones and zeros are more or less the same. Okay? Which does not give the attacker any particular, precedence of ones over zeros or zeros over ones. And this is the first test that usually NEST recommends, is that if you have any random sequence, okay, what are the number of zeros, what are the number of ones? If they found that like the distribution is really has certain gap, then this is not good. That technique is not good. Okay? So independence means that the different parts of the key are statistically independent. So knowing any part of the key will not allow you by any chance to predict any other parts of the key. Okay? So the general strategy is to apply the number of tests until confidence that independence exists is sufficiently strong, which means that you will generate multiple, multiple key sequence, and then you try to see or measure the correlation between the different parts. Like if I have 1 0 and 0 1, how many times I have this pattern in all the random sequences? Okay, how many times do I have like different combinations or different patterns? Whether it's 1 0 0 1, 1 1 0 0, things like that. So I do multiple tests like this until I get some level of confidence that indeed the different parts of the key are statistically independent. There is no correlation between the different parts of the key. So that's a very important property. واضح? So we understand the properties now. So they are now. So this is the unpredictability in applications such as reciprocal authentication. Reciprocal authentication here means that if you have two parties communicating together, there is the concept of message authentication, which is, we are going to study that today. So message authentication here means that, of course, we talked about user authentication, right? Or peer entity authentication, which means that we authenticate ourselves, one, for the entire connection. It's like you are authenticating yourself to a website only once at the beginning, and that's it. But behind the scene, every single message that you have to send to the receiver, it has some sort of message level authentication. Every single message has to be authenticated, which means that it has the fingerprint of the origin, okay, which is what we call origin-based authentication. Now we talked about origin-based authentication. So every single message has to fingerprint the origin in it, and the receiver should be able to recognize and identify that this is indeed coming from that origin and not from anyone else. Okay? Reciprocal authentication here talks about the fact that, you know, if I'm sending the Bob a certain message, so Bob should be able to authenticate this message that is coming from Alice. At the same time, any response that, you know, goes back to Alice, Alice should also authenticate this message that indeed is coming from Bob, and so on. So this, by this we mean this is what we mean by reciprocal authentication. So this reciprocal authentication it's another mechanism that we'll talk about in a few minutes, and that uses also some random sequence. So with true random sequence, each number is statistically independent of other numbers, as we have talked about, and care must be taken that an opponent not to be able to predict any future elements, even if he or she knows parts of the key, independence or the unpredictability that we talked about. Okay, so these are the different types of random number generators. There are three common types. Okay, the first type here is what we call true random number generator. True random number generator. This means that the other one are not true. Yes, we'll call it pseudo. Pseudo means يعني semi random number generator, right? Anything that's not using a natural source of true randomness, is considered pseudo random number generator. We'll talk about the properties of this. But the first type here is what we call a true random number generator. And these techniques, what they do is that they take a source of true random from the nature, okay? And what they do is that they just convert it to A to D, that's it. So what is the source of randomness from the nature? There are multiple of them. Okay, there are many of them. One clear example is wireless channels. Okay, wireless channels. If any of you is familiar with maybe Muhammad knows it, physical layer security. So physical layer security uses that property, uses the randomness of channel. And the good news as well is that this randomness is reciprocal as well, which means that if Alice is sending to Bob, the wireless channel in between them is unique to both of them, and it's actually reciprocal, which means that whatever the communication from Alice to Bob, that this type of communication encounters across the wireless channel, on the way back, it will encounter the same performance. And this is very good property of any wireless channel. So we can use wireless channel as a random source. In some cases, of course, here, we do more than just A to D. We do other things. In some cases, the random sequence does not exactly fulfill 100% the two properties. Okay? But we have also other techniques called scrambling techniques. So we can use scrambling techniques, okay, to kind of manipulate the byte stream that comes from that true random source and make it true random. Okay? There are many examples. Hardware it has some properties that are in somewhat like CPU heat the heat of the CPU is somewhat random, something that you cannot predict. So if you measure the heat of the hardware or the CPU and convert it to binary, okay, and then you can do some manipulation to make it true random. That's one way of doing it.
Isn't that also based on what processes you're doing and running?
Yes, but which is, this is the unpredictability of it, is that you don't have any control what the CPU is currently processing, in which case you don't have any prediction how the temperature will change. It depends on so many things. Depends on weather, it depends on how loaded it is, it depends on so many things. Okay. In some cases also, some people claim مثلا that stocks they are true random generator, because if you can predict them, then people will lose. So somehow they have to keep it really true random. Otherwise, although some people have done some effort to really predict stocks, but these predictors, they have, until now they have, in my opinion at least, they have low level of accuracy, or they don't have good level of accuracy. Otherwise, many people will lose. So anyway, true random source from nature, convert to binary, and that's it. That's one type. Once we have here random byte sequence, we'll see that most of them, they use byte sequence. We'll talk about one of them. Then these bytes, we can take them, we can do all sorts of things. We can use it as a key, we can use it for authentication, for initial vectors, many things. Okay? The other type here, which is what we call pseudo-random. By pseudo-random here, it's semi-random, okay? And usually these types of techniques, they take a seed. Okay, we call it a seed. Of course, we are all familiar with it. We have used these pseudo-random generators, I hope, in programming and in simulations and in many things. ماشي? But we have to notice here is that this algorithm is actually deterministic. This is the key here. The algorithm is known. Okay? The algorithm itself is not random. It's a deterministic algorithm, but it takes the seed. The seed itself is an arbitrary number. Okay? I don't want to confuse you and say that in some cases we use key as a seed. We'll talk about this later. But the seed is any arbitrary number. So if you start, because this is a deterministic algorithm, okay, this is very important that if we start from the same seed to generate a certain byte sequence, okay, at two different locations, will we get the same random sequence or not? Yes. Why? Because the algorithm is deterministic, is well known, right? And that's very important property. We could use that for communication. So, for example, if we can use Alice and Bob, they can use a random sequence, but using the same seed. So somehow they agree on the seed. Okay? How do they agree on the seed? We'll talk about that. But somehow they have the same seed. They started from the same seed. And they have generated some random sequence with a predefined size of bytes. Okay? So the generated random sequence will be equal, will be identical on both sides. You had a question? For this particular thing, because if you use true random at two different locations, you don't have any guarantee that the random sequence will be the same here. But in some cases, we need it to be the same. So it fulfills the two properties. But at both locations, it should be the same. Okay? And another very important property here, by the way, reversibility is not a condition here. In fact, it should not be computationally feasible. Which means that if I have the random sequence, if I look at it, can I go back to the seed? That should not be easy. It's not a condition here. In other words, if I want to use it between two different locations, both of them, they use one way of generating the same random sequence. But there is no requirement that from this random sequence, I send it to the other side and the other side will reverse it back. No, there's no such requirement. This is very important, by the way. Encryption algorithms, reversibility is a condition, صح? We talked about reversibility as a condition. And that's why we even talked about some things that need to be fulfilled in مثلا this algorithm in order to guarantee that the reversibility is possible. ماشي? But here, no, it's not a condition. In fact, it should be hard, and I will tell you why in a minute. Okay, because this random sequence can be generated or guessed on the other side, but even if you guess the random sequence, that doesn't allow you to easily say, okay, so we started from that seed. Okay, we'll talk about an example like this. The third one is pseudo-random function. This pseudo-random function, it doesn't take only the seed. It takes the seed plus some context-specific values. Context-specific values. So we said that seed is like arbitrary number, which could be the key. Context-specific values, this depends on the context. بمعنى, and it's not fixed like the seed. No, it could be مثلا, it could be, for example, the timestamp at this point. Okay? So assuming that مثلا Alice and Bob, okay, they are using the same seed, but they want to make it harder, so they can use the timestamp at this point, which means that there is some synchronization between them. They take it as the exact same time, مثلا. Okay? And they combine this with the seed and use what we call a pseudo-random function. This pseudo-random function will be used a lot, and this is what we typically use to generate initial vectors and other things for the security services, as we will talk in future chapters. The most common one is the pseudo-random function, and we'll talk about why. Because, well, we said that reversibility is not required, but we'll see that like this is one of the things that we use مثلا to break Wi-Fi easily. One of the protocols of Wi-Fi, okay, it's based on RC4, which is the one that we'll talk about in the next slide. So RC4 uses random sequence, okay? And Vernam cipher, very easy, Vernam cipher. And we said Vernam cipher, I can easily, if I predict a simple, plain text, I can break Vernam cipher in one step. But this will allow me to get not the plain text or not the key, it will allow me to get the random sequence. But the idea is that if I get these random sequences at different points, okay, I can use that to more and more be able to predict the seed. And the seed here for me, as we will see in a minute, is actually the plain text. Or the key, sorry, not the plain text, the key, sorry. Okay, once I know the key, خلاص, I broke the communication. So in order to make this harder and harder, we can add a timestamp with the seed to make it harder and harder.
The output's going back again as an input. Is this like happening in each long, or it's like?
Yes, we'll see that. We'll see that in a minute in the next slide. Yes, so there are multiple steps that are done recursively. So recursion is actually part of this. And this is the way and that's the main property by which we can generate the random sequence of any size. By the way, one of the properties, this is a good point, one of the properties here is that the size of the output is not necessarily related to the size of the seed.
Are we doing hash here?
No. Hash is a totally different thing. And usually the seed has a very limited length. Let's say 16 bytes, like the ASCII مثلا ولا حاجة كده. But the random sequence could have any arbitrary number. Okay? So how do I do this? By doing this recursion. Using this recursion, I can always keep generating bytes and bytes and stream of bytes. And I can do that as many times as I want.
To reach the length that
Yes, to reach any length I want, any length. And it could be like a continuous process. I could do that forever. Okay? But we'll talk about forever is actually, it's a fluffy word, but there has to be a limit. Everything has a limit. Okay, so there has to be a limit. طيب, so how can I achieve these pseudo-random number generators? We said that the algorithm itself is deterministic, right? So يعني the security people said, oh, deterministic algorithm, so okay, so we can use encryption algorithms, because encryption algorithms, what they try to achieve is they try to generate an output which has no correlation with the input. Okay? Except that here I have to customize this encryption algorithm to keep generating different outputs from the same input. And that's doable. We can do that. ماشي? The worst thing is that like the ciphertext goes back, I generate another ciphertext and so on from the encryption algorithm. We can do some sorts of mode operations. We'll talk about this. Yeah, we can generate some random sequence. Okay, the random sequence will have no correlation to the input. Okay, and we can customize it to have different sizes and so on and so forth. Okay, but encryption, they have reversibility, which I don't need. I don't need reversibility really, but I could actually use encryption algorithms. Or another purpose-built algorithms, these specific algorithms which are different from encryption, that we can use to generate this random sequence. Okay? طبعا encryption algorithm, they achieve some level of unpredictability. طبعا if they are predictable, then it's a problem. So unpredictability is implicitly guaranteed for the ciphertext. So that's why we can think of them as a source of pseudo-random generators. So we'll talk about a very specific example in that category, a specific algorithm which is specially built to generate a random sequence, which has these two very important properties, randomness and unpredictability. Okay? Okay. ماشي. Okay. So now we'll talk about a specific technique which can be used to generate arbitrary number of random bytes, okay, with any arbitrary length that you want, such that this random sequence or random bytes, they fulfill the two requirements we talked about. So this is as part of the stream cipher. As we said before, stream cipher, they have different properties with block cipher. Block ciphers, we said that you have the input text, which is like very, very large document or something, or a picture, similar to what you will encounter in the assignment. Okay, you break anything into blocks, and the block, we apply the encryption. Okay, we come up with a cipher block. Okay, so this is what we do for. So we have Alice, and we have Bob. Alice has very, very large document. Okay, Alice breaks that into blocks. Okay, each of these blocks gets transferred into a cipher block. Okay, and then these cipher blocks, they get transmitted to Bob, and Bob converts back using the decryption algorithm back to assuming that they have the same key. So this is the block cipher. Okay, stream cipher here talks about a different thing. Stream cipher talks about the fact that you have the document with any arbitrary length. Okay, what you do is that you take that document and you generate a random sequence with the same length of that arbitrary size document, and all you do is just to use the Vernam cipher. That's it. And then this is out. Okay? So, as we said before, Vernam cipher itself has good level of security properties. However, this is, you know, assuming certain assumptions or making certain assumptions, right? So the Vernam cipher indeed achieves the objective that the probability of a key taking certain value, okay, given that we have a certain ciphertext, in fact, this is equal to the probability of a key taking certain value, which means that knowing the ciphertext is not going to help you to guess the value of the key, right? So that's good. This is good. However, if we add here simply the probability of having a certain ciphertext and a plain text is pi, then what is the key? The key is in fact Ci XORed with pi. That's it. So in that case, it's O of 1. All right? So as long as you don't know any plain text, then it's good. If you know one plain text, then it's done. You can get the key, can guess the key in one step. Okay? So what they try to achieve here is that, of course, what we have here is not the key, it's actually the A. This is what? This is the random sequence, not the key. Okay? So what you can guess here, even if you know a plain text, you can guess part of the random sequence. And this part of the random sequence hopefully will not allow you to easily reverse it back to know the actual key. Okay? So the key will use it as a seed for a pseudo-random generator. Okay? Then we can generate the output with any arbitrary length we want. In fact, it's actually done in a streaming way, which means that we generate byte by byte, as we will see in a minute. We generate byte by byte. And for each byte, we XOR it with 1 byte from the document, and then we send it. Okay? Then we send it to the protocol. The protocol back can send it in any way. TCP, UDP, whatever. واضح كده؟ So this is why the stream ciphers, they have يعني good property and bad property. So the block ciphers, they are very strong property from the security perspective. يعني the security properties of the block ciphers are actually very good. Why? Because knowing the ciphertext, okay, because of the fact that the ciphertext has no correlation with the plain text or the key, okay, has no correlation whatsoever, will make it hard for you to guess the key. And this is achieved by many kind of permutations, manipulations, you know, mixed columns, things like that. Okay? So we do multiple rounds of this that makes the correlation of the output with any input, whether it's the key or the plain text, makes it really, really not there, and hence it's very hard for the attacker to guess the key. However, we can, in fact, guess or recognize different parts of the random sequence here, okay, using the particular weakness in the Vernam cipher. Okay? By guessing different parts of the random sequence, if we do many of them, then there are certain well-established techniques that allows you to guess the actual seed, or in our case, this is the key. So because of the fact that different parts of this random sequence can be recognized easily, okay, if you have enough number of them, this allows you to get to the key and break the communication. So on the other side, the stream ciphers are weaker at least, relatively speaking. They are weaker in terms of security properties. Okay? So the question now, if they are weaker, why do we use them? What do you think? Because they are in fact being used.
Faster.
Faster, bravo عليك. As we will see in a minute, the technique for generating this, the only complexity is here. Because XOR is like, the complexity is negligible, right? So the complexity is here, and as we will see in a minute, the complexity of the pseudo-random generator is very, very low. But there is another reason, there is another reason. Real-time communication, and what is the property that has to do with the real-time communication? They are more tolerable to channel errors. Okay, they are more tolerable to the channel errors, and you will encounter this. You will be able to see this in the assignment. Like if I give you a picture, I tell you, okay, transfer this picture using block ciphers. You will divide it into blocks, okay, and then you will send it over the channel. So what if the channel is erroneous? Erroneous, which means that the channel introduces certain error. This is not an attack. These are certain errors. So this means that in one or two of these blocks or of these cipher blocks, there is an error introduced by the wireless properties of the channel, by the impairments of the channel, right? So if that error is introduced to the ciphertext, can you imagine if we do the decryption? The decryption has to do what? Has to do like the permutations, the substitutions, in reverse direction. Okay? So this simple error can cause many errors in the plain text that you will get on Bob's side. واضحة دي? Okay? So one simple error in the ciphertext can propagate many errors in the decrypted block at Bob's side. Okay? But because of the fact that stream ciphers, they use Vernam cipher, which means that if I have an output sequence of bytes, okay, and then there is certain error, okay, here and here. On the way back, what will happen? This error will still be localized in the decrypted text or in the decrypted document on both sides. Why? Because here we don't do actually many permutations and substitutions. No, we just generate a random sequence and we XOR. That's it. So the error will not propagate, will not cause error propagation. واضحة؟ في حد مش فاهم؟ واضحة؟ في حد مش فاهم؟ أنت مش فاهم؟ It's not clear. No. منى واضحة؟ Okay. All right. So that's a cool property in the stream ciphers. So stream ciphers are tolerable to errors, okay, but they are weaker in security properties. So, subhanallah, there is no free lunch. You work on something, you break another thing. Nothing is perfect, okay? So these are the properties. So the encryption sequence should have a large period. And what that means is that, you know, we're saying that we can generate random sequence as long as we want, right? Even forever. But what will happen if the random sequence really grows forever? After huge amount of byte sequence, okay, you will start breaking the properties of this random sequence. Because it makes sense, you have a very limited length and you're using this length to generate bytes forever. After a certain number of bytes, you will start to have predictable patterns. Because remember, the technique is deterministic. And the seed is limited by the size. So after some time, you will hit the physics, right? You will hit the physical properties that will prohibit you from really innovating true random bytes, okay? So the generated random sequence, although there is no specific limit, but after some time, it becomes useless. It becomes predictable, it becomes not true random, and so on. Okay? So if you want more random sequence size, you should make the seed longer. Okay? So the longer the period of repeat, the more difficult it will be to do the cryptanalysis, right? So because cryptanalysis, it does work back on the predictability of the sequence on these things. Okay, so after huge amount of trials, you will start to, out of your hand you start to have مثلا more ones أكتر من zeros. You will start to have like some repeated patterns. Okay, and that will break the properties of the true random source. This is what we are talking about, so that the key stream should approximate the properties, and we say approximate because it cannot achieve it 100% regardless of the size. So there is a limit. The more random appearing the key stream is, the more randomized the ciphertext is, and that's why if we need the ciphertext or if we need the random sequence to be very, very large, then we need to increase the size of the key or the seed. So the pseudo-random number generator is conditioned on the value of the input key. So to guard against brute force attacks, the key needs to be sufficiently long. Why is this? Why we didn't talk about this in block ciphers? Because in block ciphers, the key size is fixed. And the block cipher size, or the cipher text size, is also fixed. And the plain text everything is fixed because it's block based. But here, we have the flexibility to increase the key size, reduce the key size as we see appropriate. We can increase the random sequence. Okay. Here, increasing the random sequence means that after a certain time, we have to use another key, all right, to really guarantee the properties of the random sequence being true random. So if you want to make the random sequence really random for a long period of time, then you have to keep changing the key. Why don't we do this every second? Why do you think we cannot renew the key every second? Well, we can do that.
Because it's symmetric.
Yes. So when we say changing the key, now we're saying it easy, but this comes with a cost. The cost is key distribution. We'll talk about key distribution later. There's a cost associated to this. So we cannot just say, okay, change the key for every packet. It's not easier said than done. Yeah. There is a cost associated with this. So with the current technology, the typical key size is 128, which is equal to the AES key size, and it's longer compared to this. So this is the standard stream cipher, which is recommended by NIST. It's called RC4. RC4 is named after Ron Rivest for RSA security, and Ron Rivest also the name is clear. All of them, all the names are very clear, yeah, from a particular region, yeah. So it is variable size stream cipher with byte-oriented operations, and we'll see how we can generate recursively, how we can generate any random sequence with arbitrary size. The algorithm is based on the use of the random permutations, and this actually is being used in multiple services until today, even though we are saying that the security properties is a bit weak. And in fact, there is always an assignment which I'm attracted to give you, like as a challenge. It's not a challenge, actually. It's how to break the Wi-Fi. So you can break into Wi-Fi easily by running, but because of the fact that the tool is already there and you just need to run it, makes it really a trivial assignment. But it's already there. And it's based on the fact that you can try to guess different parts of the random sequence. As we said, the more random sequence parts you can generate, you can easily use that to guess the key. There is like some correlation between them, so it's well established. So SSL, or secure socket layer, as part of the transport layer, will study that security service in details. So this is one protocol that uses RC4 as the standard. And of course, there is the wired equivalent privacy. Also, we'll study that as part of the network access security. Okay, so of course, SSL is transport layer security, and WEP is network access security in lower layer. Okay, so we'll study those two protocols, and we'll talk about how we can break RC4. Okay, so that's how RC4 works. RC4 is based on ASCII codes. We know ASCII codes. We know that the alphabets, they are all the possible characters. It can be encoded using 256 different codes, right? So each of these codes represent a certain letter or number or keystroke or anything like that. So we are all familiar with the ASCII codes. So we have this is like sort of a dictionary of all the characters that we can use. And these are the bytes that we are trying to take one of them using certain permutation and generate it such that if you know any byte, you cannot guess the other one, okay? And if you calculate the number of ones and zeros, you will find them equal. These are the two properties we are trying to achieve. So to do that, again, here, as you see, this is the key length, and we don't specify any key length because anything is possible. Anything is possible, okay? So the algorithm here is based on three. تفضل. No. That's different. No. Certificates use public cryptography. We'll talk about this. This is different. Okay, so the key length, again, is of arbitrary size. We don't specify the key size. Okay, although typically in the standard, they typically use 128. But it's not a condition. You can use any key size. And it's based on 3 steps. The first step and the second step are done using for loop from 0 to 255, 256 times. So the loop itself is done 256 times. Okay. So for the initial state here, we create the t vector, and this t vector is of length 256, same size like the s vector. So what we do here is that the t of I equals to t of I equals to s. So we're trying to take any byte of the s vector and put it in the t vector. And here this step is very easy. We just take the key and replicate it multiple times, okay, to get the t vector. So it's easily s of I mod key length. Okay? So we take this byte and we put it here. We take this byte and put it here, and we take this byte, the key itself, not the s, the key itself. We put it here, here, and then we repeat it multiple times. Okay? So this is key, sorry. This is k, sorry. This is the key. Until now, we didn't use s at all. So in this step, we don't use s. Okay? So the t is based on replicating the key multiple times. So this is the initial state. In step B, we start using the s value. And what we do is that we calculate the index of the value j. And value j here starts with 0, okay? And then each time j changes. And what we do here is that we are trying to swap 2 bytes in the s vector based on a function of the t vector. So we're trying to swap 2 bytes. Every step, we're trying to swap 2 bytes. It's like we're trying to scramble s, okay, based on the values in t, which is based on the key. Okay? And here the function is very simple. So j equals j plus si plus ti. So this will give you the index that you will switch with the the current I. So you start from I equals 0, okay? So I want to know the value of this S at 0. So this value needs to be swapped with another byte. Which byte? Based on this. So I try to calculate this, and then I take the value in this byte, and I switch it with the value in the 0 index. Okay? And then I increment I, and then I see the new value of j, and I keep doing that. I keep doing this fixed number of times equal to 256. So this initial permutation is done for, again, 256 times. That's it. But we said that the output is of arbitrary size, right? So that's this step. This step is while true. This particular step is while true, which means that the length here can get as long as you want. Okay? So this step is the stream generation. Stream معناها you can generate any byte stream. And again here, what we do is that we do another level of permutation, but this time while true. So again, j starts from 0, and then every time it changes. J equals j plus si, and then we swap. And we keep doing that recursively forever. Okay? So for every step, we output that byte. For every step, we swap, and we output that byte. So the byte here is the current stream byte that you will output as part of the random sequence. And we keep doing that forever, as long as you want. ماشي كده؟ As you can see, these 3 steps can be done in software يعني in fact you will see the code يعني it's like 4 lines. 4 lines of code يعني حاجة صغيرة جدا. In Python it's like 4 or 5 lines of code. So you can do that. طبعا analytically you can verify the 2 properties اللي هم ال randomness and the unpredictability based on the generated byte stream. Okay. So that's RC4. RC4 is very simple. You generate a random sequence and then you XOR it with the input, and that's it. So every byte generated, it gets XORed with a byte in the text, and that's it. ماشي? Any questions? Another thing is that, as we said, one of the properties of block cipher is that it's not tolerable to channel errors, but it's very resistive to attacks, right? So can we actually achieve a behavior similar to the stream cipher, which means that the generated blocks will be more tolerable to the channel errors, while actually preserving the properties of the attack resistance? Okay, that's one of the objectives, or one of the things that they try to achieve using what we call cipher block modes. In cipher block modes, we will use block ciphers, okay, but we will try to use the security properties of these block ciphers and try to make it behave like a stream cipher. Okay? So we'll see how we can do that. So we don't apply the encryption and decryption directly to the plain text. We have to use a different way of looking at this. So a symmetric cipher processes one block of data at a time, like it's one block at a time. What the block modes try to do is that they try to do it in a pipeline fashion, to either increase the security properties or make the output more tolerable to channel errors. We'll see that. In the assignment, by the way, you will do this block modes of operations as part of AES. So the block modes of operation assumes any kind of encryption technique. Doesn't matter whether it's AES, DES, triple DES, But of course, block cipher يعني. It works on block ciphers, not stream ciphers. So it doesn't matter which cipher technique you use. It applies on anything. So for longer amount of plain text, it is necessary to break the plain text into B bits blocks. We'll see why we do this. Why we will do this. This is called cipher feedback mode. Okay, so we'll take the plain text and we'll take only part of it, not all of it, and we'll see why. So modes of operation have been defined by NIST, intended to cover virtually all possible applications and encryptions, and intended for use with asymmetric block cipher. So they don't work on stream cipher, okay? Including DES, triple DES, AES, anything. So these are, this is one of the modes of operation. It's called cipher blockchaining. In cipher blockchaining, what it tries to do is that here we have the plain text, and then we do the encryption, normal, and we go with we come up with the cipher text. But as you can see, for every step, okay, we actually take the cipher text from the previous step, and we XOR it with the plain text. And what this tries to do is that it tries to make this cipher text as a function not only of the current plain text, but also with the previous cipher text. So it makes the encryption in a chained way. That's why it's called a blockchaining. So what is the properties of this? In terms of security, do you think this is stronger or weaker? Stronger. صح. صح. Now the attacker needs to defy or needs to be challenged that the unknowns here are in fact the key, the plain text, and in fact the previous cipher text as well. And it's a combination of all of these. So in terms of security properties, it's stronger. In terms of error tolerance, is it worse or better? Much worse, right? So one error in one cipher text will in fact cause problems in all the upcoming ones. صح? Because all the upcoming ones are dependent on this one, are dependent on this cipher text, right? So if there is one error in one of the cipher text, it actually propagates. You will see that in the assignment. So in cipher block chaining, here the objective is to strengthen the security, not to strengthen the error tolerance. Okay. So, of course, in the initial step, we don't have a previous cipher text, right? So here, we don't have a previous cipher text. So what we do is that this is one of the ways that we need some arbitrary cipher text. So we use what we call initial vector. It's like when you use a variable, you have to initialize the variable, right? So we don't have a cipher text, so we have the concept of initial vectors. Initial vectors are arbitrary generated sequence, which can be generated from a random sequence, any random generator, okay? And we use that arbitrarily to act or behave like a previous cipher text, because at time 0 we don't have a cipher text. All right? Okay, so this is cipher blockchaining. Another one here, and this is a little bit complicated, and it tries to achieve some objectives related to security and things like that. But we apply the encryption this time, but not to the plain text. Okay, we don't actually use the encryption for the plain text. We use the encryption for the initial vector or part of the input after doing some circular shift or left shift to the text. So what we do here is that we encrypt And then we take only S bits and we discard the remaining bits. And these S bits, they get XORed with only S bits from the plain text. So here, the big document is actually divided into a block, and we only have half the block. So we apply this for half the block, which means that, as you will see in the assignment, the complexity here is double. The complexity for the cipher block mode, cipher feedback mode, is actually double the complexity of any other mode of operation. And you will see that, because in the assignment you will be able to calculate the complexity, the time consumption, and the error probabilities, or error, the error that's caused by applying certain mode of operation. Okay, and we then take this cipher text and we shift the input and we put the S bits. So we feed the S bits from the right, and then we apply the encryption again. And then we take S bits from the plain text too, and so on. And we keep doing this. This is called cipher feedback mode. Okay? The properties of this is highly dependent on this number of S bits. تفضل.
It works on bit manipulation.
هو yes, yeah, هو طبعا ما هو البلوck ciphers, they can work on bit level manipulation. So here this S bits, it's not specified whether it's like half the block or 1/4, or it's up to you. In the assignment, we'll make it simple and make it like half the block. So the behavior and the properties are highly dependent on the size of this S bits. And usually the size of the S bits is less than the block size, definitely. It has to be less than the block size. Okay? And usually it's half or 1/3 or something like this. So this is the cipher feedback mode. And because of the fact that this is the first trial to try to give the block cipher a behavior that looks like stream cipher. And why is this? Because as you can see, applying the encryption to the plain text is done through Vernam cipher. Here, so it's as if you are trying to use the encryption technique to generate some kind of random text. And then you XOR it to the plain text. But here in the cipher feedback mode, okay, they tried to achieve that, but unfortunately they lost on the complexity because of the fact that the random sequence that you are trying to generate here, it gets applied to only S bits because of the fact that this has to be shifted and so on. Because of this mechanism, we lost on the complexity. So here, in the cipher feedback mode, you will see in the assignment that in terms of error tolerance, cipher feedback mode is much better compared to the cipher block chaining. You will see that. Okay? But the complexity is high. Here, the complexity is high. So we tried to gain on one aspect, but we lost on another aspect. ماشي? That's the compromise bar. The counter mode, as you can see, is simple. It's actually, it tries to achieve just what we said. So instead of applying the encryption to the initial vector or to a circular shift or something like this, they simply use counters. So they encrypt counters, okay, using it as a seed. And this will allow us, using the key, to use the encryption algorithm to generate some kind of, again, random sequence. And then we XOR it. And here, as you can see, it applies to the entire plain text. So no S bits anymore. Okay? So this really, and there's no chaining here, remember, there's no chaining here, which means that this cipher text is based on the plain text and is based on the key. And a counter which can be somewhat guessed, but it's fine because we use that as a seed to generate a random sequence. Okay. So as you can see, the modes of operation, they try to achieve the objective of RC4 in a way by generating like some kind of uncorrelated output, which looks like a random sequence, and then at the end we use Vernam cipher. This allows this counter mode to be very much error tolerant. Okay, assuming that using this encryption technique as the random generator, it makes it more complex, and in this way we are actually making the security properties stronger. So this tries to achieve a trade-off between the two. But the encryption algorithms is much complex compared to the random generator that we just talked about. So these are not 4 lines of code, as we said. These are more complex than that. They do permutations. But the good thing is that if we use an efficient technique like AES, which is what we talked about, so AES tries to really achieve higher efficiency, and you will see that in the assignment. You will see that the complexity is very much comparable to RC4, because RC4 is very fast. Using AES, okay, here, with a certain mode of operation like counter mode, will have more or less the same complexity, and hopefully AES will give you more security strength, and the counter mode will have more error tolerance. And that's why you will notice later on in many of the security services that we will study in future chapters, you will see counter mode being mentioned a lot because of these properties. So it tries to achieve the error tolerance with security strength. It tries to achieve that compromise. So the advantage of the counter mode. So counter mode has some advantages. Of course, especially if you use technique like AES, it becomes hardware efficient, software efficient, almost equally. Encryption can be done also, the good thing is that there's no chaining here, because chaining prohibits the parallelism, صح? So you always have to wait for ciphertext I in order to do ciphertext I+1, صح? Because it's dependent. So you always have to wait, and you have to do it sequentially. But counter mode tries to break that. There's no chaining. Okay, so in that case, parallelism is high. And if you use AES, it becomes efficient software and hardware. And in terms of pre-processing, the execution of the underlying encryption algorithm does not depend on the input plain text or ciphertext. It depends on what counter. What we encrypt is actually the counter. Okay, not the plain text, or not the ciphertext of the previous step. It's just a simple counter, right? And we just XOR. We use XOR, which is the Vernam cipher, which allows it to be to greatly enhancing throughput. Throughput here معناه ايه؟ If you remember throughput from networking, throughput معناه ايه؟ The amount of information that arrives successfully on the receiver side, which means that implicitly that this is error tolerant. It tolerates the error more than the block ciphers, because block ciphers, any simple error will corrupt everything. But here the throughput will be much higher because of the fact that errors will be localized. Okay? طبعا الكلمة نفسها implicit شوية, but hopefully we explain that in a clearer way. Okay? Random access here also is based on the fact that random access, the I's block, plain text or ciphertext can be processed in random access. يعني what does that mean? I can choose to reconstruct plain text number 100, right? Without having to wait for anyone. I can do that. If I want, I can do this. I have blocks of ciphertext. I can choose to select any one of them and convert it without having to really decrypt any other block. So they are not dependent. Okay? Independence allows for random access. Provable security, so security strength is high, and simplicity. It's just based on XOR. ماشي كده؟ All right, so this is a summary of this chapter. So we talked about symmetric encryption, we talked about cryptography, we talked about the crypto analysis, the difference between crypto analysis and the brute force. We talked about the fuzzy structure and what are the properties of the fuzzy structure. We talked about specific symmetric block ciphers such as DES, triple DES, AES. We talked about random generators and the different types of them. We talked about RC4 being one of the standards that NIST recommends that use pseudo-random generators and use the stream cipher concept and the properties of this. And we talked about the modes of operation, including cipher block chaining and cipher feedback mode and the counter mode. Okay? So the assignment actually digs a lot into this chapter, so you will be able to do some hands-on work that will allow you to understand all these techniques in a lot more details. Okay? Any questions? Should we move on or?